Here we are. Okay, good morning. So last time, brief summary of what we saw last few times. Well, there's the way arrays, more or less, you can think more or less of arrays storage in the RAM memory, a one-dimensional array. In this first example, you have some storage space for variables and somewhere there's a reference to the actual object, and the actual object is composed of some preliminary information, which I'm calling the header, and then the actual data, which is all in one contiguous chunk of memory. Okay, so this is, and then if you have a two-dimensional array, it's still one chunk of memory, but it's the job of the header to keep track of the number of dimensions and the shape, and from this information here, you can restore basically the table-like organization of the thing. So how much? So for example, the fact that in this example there's the first row and then the second row, and you just know how much memory the first row occupies, because you know that each row is of length 3 in this example, and it's made of 64 bits per element. So 64 bits times 3, that's the storage for the first row, and then the second row, and so on. Okay, so also, this was just another example. Also, then we started implementing the a small code to do some Monte Carlo tests. We also briefly saw the speed test to demonstrate that indeed NumPy is faster, provided you can use it if you don't do things like using normal sum instead of NP sum. Then it becomes slower than before. But as long as you use NumPy functions, it can be 10 times as fast at least, or something like that. Now, I haven't mentioned this last time, but this is a very important thing that I want to point out right now. So you see here that I have basically a for loop, and this is the comprehension with a for loop inside. So this is the standard Python way, right? And here, on the other hand, I have a single function which just creates a whole array with n elements inside it. Now, okay, now, this one is faster, okay? But it's not faster in any fundamental way, not in a theoretical sense, let me put it this way. So if you do a theoretical analysis in terms of the scaling of how long it takes as a function of the size of the thing, so the big O notation, right? So this is still, of course, an order n operation. You write it in one line, but it still takes, I mean, I have an echo, but let me check. I don't know, maybe it's this. I don't know. So it's still an operation that the longer is the array, the longer it takes this operation. Okay, it's in proportion to the size. It's not magic. It's just that each single. So it's still there's still a for loop inside. There's no magic. Okay, and all of these operations are like this. Even sum, for example, there's basically, in order to compute the sum of an array in general, there's just nothing else to do than looking one element at a time and just summing them all up. And so, of course, this takes order n. Okay, and if you double the size of the array, the time that it requires doubles, more or less. Okay, this is obvious, but it should be pointed out because it's easy to forget. Because now you write things in one line, and you forget that it's actually that hidden in that line. There are for loops. It's just that those for loops have been written by the authors of the NumPy library in a different language, which is faster, and they're working on a better arrangement in memory and so on. So it's a constant reduction in time. So but the scaling is the same. So NumPy better theoretical scalings, let's say. But it helps in practice. Now, so the same, of course, goes here. Look at here. We have this loop. Here we have just one line, 2 lines actually, but they're say equivalent. Again, order n operation. This one, of course, order n operation. Okay, good. So, and also in this Monte Carlo code that we were looking at, we've seen another constructor. So we are speaking also about constructors. And I forgot to bring out my slides, which I'll do right now. So, okay. Here we go. Okay, so we started looking at a few functions. I said that there are ways to construct arrays without going through lists first. And the basic one, the most basic one, this one you must really know well, also the other one, but this is the basic one, it's zeros. Okay, and it creates an array just filled with zeros. And you can specify which type of elements you want by writing the argument dtype and then some type. Okay. Also, now in practice, we've seen this one, linspace, which creates, here an array with regular spacings between one starting point and an end point included, and you divide it up in a number of equally spaced intervals. And we have seen if you think about it, this one is also a constructor. Okay, because that just gives you a new array as a result. It's just filled with random numbers. Good. So this is, I think, enough for a summary. And remember that what we were trying to do with this code was to try to, the first thing we did was plotting this quarter circle, but then now what remains to be done is to extract random points uniformly in the square, and then try to use this little formula here to see if we can get an estimate of the constant pi and how it goes. Okay, any questions about this so far? No? Everything good? Good. Okay, so this is the... Now, what's the most natural way that you will do this task? So I'm saying the task is just extract a number of points, so that you decide in advance how many, I don't know, 100, 1 million, something. You extract a number of points in the square, okay, uniformly spaced. How would you do that in the most natural way? Okay, lots of shy people here, but the thing is, you just extract them one at a time. I suppose that the first thing that comes to mind, right? Which basically means a for loop, okay? You start a loop, and for a number of points, you just extract 2 coordinates, okay? And then that's point. And then after that, once you have the coordinates, you can also say, ask yourself, are these inside this area? So should we count them in the numerator, or are they outside, and should we just count them only in the denominator? And this would be the straightforward way. And of course, this works, but there's a better way. That's why I'm telling you. Okay, so the straightforward way would be something like this. You set up the number of points, let's say 100 to start from, and then you do some for loop for I in range and points. Okay, and then, well, you say, well, I'm extracting a value. Let me call it px, say the x value of the point. And how do you extract a random point? It looks like my microphone is coming and going. I hope everything works for those at home. Otherwise, let me know. So how do you extract a random? We need a random coordinate between 0 and 1, and we have a function for that. We've seen np random, right? np random. This, as we said last time, you do just once, and it works just like even regular Python random module. Okay, so we could use this, and this gives us a coordinate in one dimension, and this one gives us a random coordinate in another dimension. And then we need to check whether the point that we have now is inside the quarter circle or not. And how do you determine that? The point is somewhere here. Okay, there's some point here, or perhaps here. And how you distinguish those? Yes? Okay, both coordinates must be greater than between 0 and 1, but that's our assumption. I mean, that's how we generate them. Even this point here, the one outside, you look at this, you see, that one is still, I mean, the x is between 0 and 1, the y is between 0 and 1. But it's outside the circle. The distance from the origin, yes.
The square root of the sum of the squares.
Yes. Exactly. So if you have a point, you look at the distance from the origin. So this distance here is smaller than 1, and this distance here is larger than 1, right? And so you just need to check for a point. You need to check whether the px, let me call it this way so that it's similar to the code, squared plus the py squared, square root, this is the distance. You check if it's smaller or equal than 1. And then if that's the case, you count it up in the numerator. Okay, so let's write that. Now, if we have the square root, do we have the square root in Python? No. Not really, not directly. There's one in math, but we're going to use the NP1. Doesn't really matter at this point. Px squared plus py squared less or equal than 1. Then what? We need to somehow count it. So we need a counter, yes. So we need n inside, perhaps. So we need to count up how many points we have inside. And so n inside plus equal 1. Oops, sorry. And that's it, basically. So now we have estimated pi is equal to 4 times the number of points inside divided by the total number of points. And we can print it. So we can have estimated pi equal est pi in, sorry, okay, good. So, and then just for comparison, the true value, or let's say a very good approximation of the true value, is found in the NumPy library, because it's just such a common constant. There's a problem here and inside. Good, I had a typo. Okay, you see this? Oh, can you all read the screen? Is it big enough? Good. So there we go. Now it says I have 100 points, and it says that pi is equal to more or less equal to 3, which of course is wrong, but not that far out. And if you run it again, you see that you get a different number every time, because it's random, of course. And you see that now with 100 point, we get 2 digits here, because it's 316 divided by 100. And you repeat it, and sometimes it's more off, sometimes it's closer, but again, more or less, okay? So how do you get better? Well, you just increase the number of points there. This is starting to get possibly a little better. 10,000 points, I'm just increasing here and running the code again with F5, okay? So here you see now this is starting to get closer, even though still sometimes, occasionally, you get quite wrong result. You can increase the number of points. At this point, you see, you start noticing that it starts getting a little bit slow. But if you want more precision, you need more points, and there, whoops. Okay, at this point, you start needing to wait a little. And if you want even more precision, of course, every time I add a 0 here, I get a factor of 10. Okay, so next point, I don't want to do it, but you can imagine. And already, but okay, you might say this is enough, or you might say I need more precision and I need it to make it quicker. So how do you do that? Well, There's one obvious thing here in this code already, without even speaking about NumPy, that we're doing, that it's completely useless and it's a waste. Okay, what is it? We could already save a little bit of time here. Any guess? So, isn't the square root a bit useless? Yes. Okay, so yes, indeed, because the square root is a monotonic function, and if the square root of something is smaller or equal than 1, then you can just take, I mean, these are both sides of this expression here are positive numbers, so you can just take the square of both and keep it, and therefore we can just simply remove this, which is not going to help a great deal, but still something. Okay, you see, we did not gain much, but at least we are, I mean, more at ease. Yes?
Can we remove the for loop by the parameter is like an array of
Yes, that's exactly what you were about to do. I wanted to build gradually towards that solution. Yes? Yes, exactly. So let's see how it works. First of all, but in order to see clearly, I hope how to get there. Okay, that's the first step, and then we'll see. In order to see clearly how to get there, let's split this for loop, into two parts. Instead of n inside, okay, so let me do this. I have px's as a list and py's as a list. And then here, first I do a loop in which I just create you know what? Let me take all the first part, I'll put it here and then comment it out. So the first version was something like this, sorry. The first version was this, okay? This is our first attempt. Let's keep it around just for reference. Now change things. Start by doing something that apparently is not useful at all, and then what's this? Px equal px's I, py equal py's I. Okay, so here I have just split basically the loop in two parts. First the generation, and then I store everything in lists, okay? You see, first I generate and I save the points, and then I just count up what's inside and what's outside. How is this useful? It's not useful at all so far, but it still should work. Let's check. It's a good practice when you have code. This is a very general thing, and it's an advice that you learn through years of experience, so please listen to me. When you are doing something, it's a very good practice to have something that at least works, okay, at the beginning. Then, and some tests, okay, that checks that everything looks okay. And then when you start to improve it, just keep the old version around in some form. In this case, it's just commented out, but that's not the best thing you might do. But in general, just keep the old version around and try to modify it. And as you modify it, try to have checkpoints in which you think everything should still work, and test it. And do tests whenever you don't know something. Do tests in the console. Okay, test everything in the console. Check your way through the code. This helps you save a lot of time. It seems paradoxical. It seems like a waste. It really, really helps saving a lot of time. Okay, because if you do all at once, then at some point you might have made a mistake, and in order to figure out where it is exactly, it's a mess. Okay, it's very hard. And this way, you save up on that. Good, so we were saying, I split up this and then this. Okay, so the important thing here about this split up is that we can split it up further. Having now divided these two, look at this code. look at the fact that this is a random number, this is a completely independent random number, we could do first all the x's and then all the y's. This is, so look at this, first all the x's and then all the y's. Oops. Okay, now this seems trivial, perhaps, in this case. Yes? Yes, sorry. Thank you. Good. Let's see if it works. Yes, good. This looks trivial, but it's only because we are sampling uniformly from the square that we can do this. Otherwise, you couldn't do this at all. Okay, because the x and y are independent if you're sampling uniformly in a square or in a rectangle, let's say in general. Okay, so now we can finally take the suggestion that was given before, because now look at what's here. What's here is precisely what we had. What's here is precisely the kind of thing that we had in the previous example, right? So we can take this, comment it out. So it's basically the same situation as here. Instead of doing a for loop, we just do one single call. And now we can substitute the lists for arrays. And do it for y's as well. Okay, now this should still work, and it's still slow. It still works, but it's still slow. So we have saved up in terms of maybe a little bit of code, but still we are not there. Okay, so yes. I'm sorry? Yes, please.
Establish a number of elements that will be randomly generated. Px s is going to be an array, and so will py s more specifically in the array. So we can raise the power to all the elements from both arrays, sum them up, and then make sure that they are all equal or less than 1. This will generate an array of Boolean.
Yes. Okay. Yes. Since people at home cannot hear you, I mean that's correct. And that's what we're going to do. And people at home, I don't think they can hear you, so I'll basically repeat what you just suggested. So the scheme here is that there's still a for loop, and if possible, in NumPy we try to avoid having explicit for loops, and it's normally more efficient to use NumPy functions that are able to work on entire arrays in bulk, keeping in mind that working in bulk, there's still a for loop hidden there somewhere, like I was saying, but it's a faster for loop. So we try to use the faster for loops of NumPy instead of the slower one of Python. Okay, that's the idea. And what it happens in practice is that we try to write things in a single line of code that then goes and delegates things to NumPy to work efficiently. So what do we do? Essentially, what we need to do is this operation. But as your colleagues were suggested, what you can do is take each of these operations and perform it in bulk, essentially, all at once, just like we did with this. So here we saw np.cos is special because it can work, it broadcasts, okay? It means it's applied element by element. The same happens if you do. Let me comment this out. And no, sorry, I'm not commenting this out yet. I want to start demonstrating things here. So I have run the file, so now I do have a px's, which is a long array. Let's bring it down back to something more manageable, like, let's say just 5 elements, sorry, 5 elements, okay. And now I have my px's. And now I have my py's, and I'm going to put myself out of the way here. Okay, so you see I have these two arrays. Now, instead of going through each element and doing the operations, I can take px's and take it all to the power of 2. And you see that just like sine and cosine, this also broadcasts. Okay, meaning that it's applied element by element. And pwise also broadcasts, of course. Now, what about the sum? Well, in NumPy, so first thing, broadcasting is not limited to np.something functions. It's also involved in regular Python operations. Secondly, this Python operation also broadcasts. The summation is applied element by element. Now, for these things, this works essentially like vectors in linear algebra. You take a vector, you take another vector, the sum of the two is just the sum element by element. But that's sort of an accident, in the sense that if you do this, I want to show you this. It's a sort of an accident because you can also do other operations like multiplication, which is not what we want to do here, but you could, if you did multiplication, two vectors, you cannot multiply them that way, okay? But in NumPy, you can. In NumPy, all these operations are by default defined to be broadcasting, which means element by element, okay? So this rule by chance happens to coincide with the mathematical linear algebra thing. In this case, it's fine. You could take the square root, although we said it's not needed. Now the important and the tricky part. We need to compare this with less equal than 1. So what we would need to do is to compare this array, element by element, with an array made of 1s. Okay, so we need to check, is this less than 1? Is this less than 1? Is this, and so on. Okay, so the thing that you can do is use a constructor. In principle, you can go and do np1s, ones of how many points of n points, and look at what happens. Not just, so maybe I'll add parentheses just to be extra super clear. Not only the exponential, the exponentiation and the summation broadcast, but also the comparisons. Now this, in this context, might seem like some natural thing, but it's very tricky, especially when you try to compare two arrays. Remember this, if you're trying to check whether two arrays are the same, and you try to do this, and maybe you have some code that does this, if, let's say, okay, this is a detour from what we are trying to do, but I'm just saying, suppose that you had two arrays somewhere in your code. And it's often the case that you want to make a decision depending on whether the two arrays have the same content, okay? And often the way you write in your code and you find yourself writing something like this, if the first array is equal to the second one. Except this doesn't work. It doesn't work because, so first of all, let's see that it doesn't work. Let's see if I'm right. Okay. There, error. Okay. Why is that? That is because this does not result. This operation does not result in a single number as you would typically expect. This is not either true or false. It's an entire array of trues and false. In this case, it's all false, but it doesn't matter. The point is that it's not a single value. And therefore, Python refuses to use it in an if statement. And the same is true for the different operator, for less equal, for less than, greater equal, or this comparison. Okay? But this one is the one that tricks you. It's the one that trips you up all the time because it's, I mean, even after years, sometimes you write that and say, I forgot. So the way you actually check whether two arrays are equal is with a special function, which is array equal. Okay. Sorry, without the equal, like that. No, like that.
Is this only for NumPy?
Okay, so this works with NumPy arrays. It actually works even for lists, but for lists it wouldn't be needed in reality, because with Python lists the quality works as you would expect. But with the NumPy arrays it doesn't, and so therefore you need an extra function to do that, which works even for comparing an array with a list if you want. But the point is that, again, since NumPy is a sort of sub-language which is fitted into Python in a sense to make it faster, it has this kind of weird intersection point where they chose that equality should broadcast for consistency with all other operations, and therefore, in order to have actual usual equality, you need another function. Okay, so this is the idea, and so keep this in mind. It's also in the slides, so explained there, and I'll give you exercises for that. But the point is that these operations here broadcast, and so now back on track. This is the kind of thing that we can use to do this comparison, the one that we had in the for loop. Now we have done all of this comparison in bulk, in a sense, all in one line of code. Now, yes? Yes, I'm getting there, but this is just a new step. And yeah, so that's exactly what I was wanting to do. Now, what this is doing is taking one array and the other array and comparing them one by one, which is what we've seen so far. Now, in fact, you can even compare an entire array with a single scalar number, and it gives you the exact same result. This is faster because we don't need to allocate all of this memory just for the purpose of the comparison. But how does this work? This is, again, one more instance of broadcasting. Broadcasting not only means doing operations element by element, but it also has another aspect, which is that of essentially trying to inflate things to match their shape. We'll see later what that means in more detail, but at this stage, it means that if you're trying to do an operation which has an array on one side and a scalar on the other side, then it's as if the scalar was replicated and inflated up to the shape of the array. And then things become, as before, performed element by element, except, so I have this in a slide. So this is the first basic thing. So where you do things element by element, right? A multiplication or a logarithm, something like this. But then this for comparison, and then this is what I'm talking about. If you have just one number, then you can think of it as if it were inflated up, expanded, to be compatible with the other one. And then after that, everything works as before. Good? So you can compare an entire array with just one number. Okay, final step. How do we count up the number? So at this point, we need to count up how many true are there. How do we do that? Yes?
np.sum.
Yes, np.sum, because remember that true is equal to 1 in Python and false is equal to 0. So counting the trues in a Boolean array is just as summing up the elements. Okay? And therefore, here we are done with np.sum of the thing, and it's 3. Okay? And so what this is doing, one line of code, is precisely substituting everything that we had before. So this here. So you see an entire for loop written in just one line of code, which not only should work, let's check back, and it's way faster. So we can add zeros here. Oops, sorry. Well, might as well. So we can add zeros, and it's still fast. Another 0. Okay, now it starts getting slower. Another 0 there. So we get, I guess we've gained a factor of at least 10 or 100 or something in between there. Okay, and Again, it's no magic, it's still for loops inside, but they're hidden here. Now, this is more compact in terms of code, and it's faster. Some might also argue that it's more intelligible. That depends on how familiar you are with broadcasting. If you're familiar with the broadcasting, you can read up this line and figure it out pretty quickly. And so having shorter code and more compact is more static, but that's debatable. It needs getting used to a little bit, but still. This is it. Okay, this general process, this a little bit of jargon which you might read around, okay, in documentation and elsewhere, and manuals and so on. So this thing, this idea of going from a for loop to single expressions like this, so like this case, substitute these for loops with this case, substituting this for loop with just one line. This is also called vectorization. It doesn't really have to do with vectors in mathematics. It sort of does because it's most useful for linear algebra, but never mind that. It's just a little bit of jargon that you might read around. If you read about vectorization, this is what it's meant, okay? And this vectorization is sort of necessary in a language like Python, which is slow, generally, if you do for loops. And it can help sometimes. In order to achieve vectorization, you need to twist things and make them really hard to understand. Maybe we will see examples of those. And that's sort of a side effect, an unfortunate side effect, but this is just it. Okay? Any questions? So if, by the way, with this many points, you start looking at the plots, I didn't plot the points. Yes, okay, so let's go back now. I forgot about that part, so let me go back. Let's go back to the plot and say that we'll go back to 100 points and say that we want to plot these points, the px's and py's. How do you do that? There's the plot function. The plot function takes an array of x values and of y values, so you can just write those. If you do this, what happens? Do I get the points? Let's see. There we go.
If we run the same thing, should we get on the pages range feature? If we run the same code?
I'm sorry. If you run the same code?
If I run the same code,
yes,
I'm going to receive a new picture, like a new slot.
Okay, so this must be a new setting in NumPy. So the way in which I achieved plotting on a different window is as follows. You go to Tools and Preferences, and then, okay, sorry. So Tools, Preferences, IPython Console, and Graphics. Okay, I'll repeat. Tools, Preferences, IPython Console, Graphics. And here, you see that the graphics backend, instead of inline, which is what you probably have, I changed it to something else like Qt5 or any of the other ones should be good. Now, unfortunately, if you do this and change these settings, you have to restart the whole Spider for it to take effect. Okay, so next time you restart Spider, you can get that if you prefer. Okay, so we were saying that this gives us lines. What does it give us line? Let's see just with 5 points. There we have 5 points. You look at the points, and you see that what it's plotting is 0, 72, 0. So the first point is this one here, okay? And then the second point is 0, 88, 0, 0, 3. So indeed, it goes here, and it draws a line between the first two. And then you go to the next point, which is 0,079, 081, which is here. And you see that it doesn't matter that the points are not sorted. PyPlot just takes whatever you give it and follows point by point drawing the lines. So we want to get, this can be useful and we will use it, but not right now. Right now it's not what we want just points. So what you do is either saying marker equal dot, okay? No, sorry. Do I have the plot CLF? Yes. It should be just this one. There we go. So I'm not sure. I mean, this has changed probably. Yes. Okay, so it used to be equivalent. Now it's not anymore, apparently. It's annoying. Anyway, so just without marker, just do this. Okay? Just write a string with a dot inside, and it uses dots. And then you can go back to 100 points, and you see that more or less you get a uniform distribution. And there we go. With 1,000 points, it gets better. And with 1 million points, of course, you cannot see anything at all at some point. There you go. It's completely filled up. See, too many points to see anything useful. But you can see that it's more or less uniformly distributed. Okay. So this was it. Now I have a few tasks for you. The first thing is that we did not draw the frame, the square. So just for the kick of it, just draw, look at my fingers, you draw a square, okay, in one single line of plot, of PyPlot with black, in black color, okay? Try to do that. It's not hard. The other thing, for the other thing, yes, so there's another task that I want to suggest to you. So first one, tasks. 1, draw the square, the 0, 1 times 0, 1 square in black in one line of code. Okay. 2, what about the 3-dimensional version? Now we have a square with a quarter circle. Suppose you had a cube, 0, 1, 0, 1, 0, 1, with an eighth of a sphere. Okay? So something like this. Something like this. Okay, you have a cube. Oh, you don't see it there. Well, possibly it was better when you didn't see it. So you have something like a sphere that intersects the faces, something like this. Okay, so you see something like this. And then you also have, of course, these, the rest of the cube. Okay, so the 0, 1 cube. And then you draw, this time you put points at random inside the cube, and you count up how many fall inside the eighth of the sphere, which should be a straightforward extension of what we just did. Now, you should now try to work out from that, from the formula. Now you need the formula for the volume of a sphere, which of course involves pi again, and you can estimate pi that way. Okay? And now you can also go and look up the formula for spheres in higher dimensions, 4, 5, 6, whatever, in Wikipedia, let's say. You look up the formula, still radius 1, still same idea, you just add more dimensions. Now if you do that, you will notice something. Oh, of course, you cannot plot that anymore in 4, 5, and so on dimensions. But first, there are a few interesting things about this. You should be noticing something that happens as you increase the dimension. Your code gets worse. I mean, at estimating pi. You need more and more points. And I would like you to think about why that is. And the formula itself has some peculiar, shows up something peculiar. And I'm mentioning this because in the context, I mean, this technique here, Monte Carlo sampling, of course, in our case, it's just an exercise, but in general, it's really useful. In general, it's really useful explicitly when you're working in very high number of dimensions. And you might want to say, well, where am I going to work in why would I ever need to work in, say, 10, 100 dimensions? Well, the answer is that in data science and in data analysis and these kind of things, it happens all the time. It's actually the most common situation. Basically, from this point on in the course, we are going to reason and live in high dimensional spaces, okay? Because each dimension might be some parameter that you want to keep under control or to want to measure of some process, complicated process that you have. And so if you have 10 parameters, you're now living in a 10-dimensional space, this sort of thing. So I know that this is a bit of a leap from where we started from, but we will see then later how, in fact, it's very common to work in large number of dimensions. And so it's interesting to go and see what happens here when you increase the number of dimensions with this little piece of code. So second task, redo in 3D, 4D, and so on. What happens? Okay, 3, and maybe we can discuss it on the forum if you have results. Just we haven't activated the forum. So, side note, we are still waiting for the forum, and I'm not sure at this point what we are waiting for. I keep sending emails to ask for it, but the thing is, if we then don't get authorization to use Piazza, we are going to use the Blackboard forum from Bocconi, which has a horrible interface, but still all the functionality that you need. So please use that in case. I will activate it if I don't hear from the higher ups, let's say, shortly. And so, yeah, if you find out something and want to discuss this aspect of what happens in 3D, 4D, and so on, we can discuss it on the forum, for example. Redoing. Okay, so another thing that you might want to do is the following. This is something, this one is also not hard, but you should try. So suppose that now, so this is high dimension, okay? High dimensionality. Now, what else? This other task is scaling. So here's what you should do. Suppose that now you make a graph with a number of points, and here you have your estimated pi. Can you see? Yes. You have your estimated pi, and of course, in this particular case, you know, oh, come on. You know that the real the true value is somewhere, I don't know, here, okay? Let me plot it. So this is the true pi. Now, if you take, say, 10, 20, 30, 40, and so on points, and you start you start running your code, you will see a point somewhere here, perhaps, and then here, and then somewhere here, and then here, and so on. You connect them up, and you should see something that goes up and down, okay, around that true value. The thing is that the more points you get, the closer you should get to the real value. So you would expect actually, if this X range is wide enough, you would expect something that does something like this, more or less, okay? Very noisy, but going, shrinking, and shrinking. So you should check that that is true. And also, if you can, find out, I mean, check also this other property, which is a general property of Monte Carlo, of this kind of Monte Carlo algorithm, that if you try and do an estimate, the width of this line as you go along, it should be somewhere proportional to 1 over the square root of n points. Something like that. Yes, you can compute the width as the difference between the maximum and the minimum, or you could do a lot of samples for each point and then compute the standard deviation, for example. You could do, I mean, any of those should more or less work. I'm not asking you to do anything very, very precise, just to check that if you can to do an estimate of this kind of stuff, okay? So you might want to compute, again, maximum minus minimum, and then plotting it as a separate plot and check whether that goes down correctly with the correct power law, okay, of the square root, something like this. Which means, of course, this scaling law, this is a proportionality sign, right? It's not an alpha, just so to be clear. Well, whatever. Maybe I can do it as, okay, something like this. It means, of course, that if you want to increase the precision by a factor of 10, you need 100 more points to multiply it. You need to spend 100 times, 100-fold time in doing the computation, which looks bad, but it's not as bad if you're working in higher dimension. In 2 dimensions, it's horrible. It's really horrible. It's not what you would do. But if you were working in 1,000 dimensions or in 1,000,000 dimensions, suddenly this becomes the better options that you have available. So, sort of, okay? So this is just something that I mentioned to mention that it's kind of useful. Okay, so this check scaling of the estimate error with endpoints. Okay, good. So so I think this is enough. Good. Any questions, comments, whatever? I was searching a bit online, and we need from MPL to import matplotlib to have a 3D graph. Okay, so sorry, there are questions before. There's one that I skipped. Does it somehow help with the approximation? I'm sorry, I skipped this question. Please, Bora, if I didn't answer by accident, please tell me what you were talking about. Increasing the dimension. Ah, no, it gets worse. It gets worse. And maybe again we can discuss on the forum why. Yeah, but what would be the reason? That's why what I'm trying to say. Just have a think about it, and then we'll discuss it later. Okay. So the other question is, if we want to have a 3D graph, yes, you need some special MPL toolkits, import matplotlib 3D. We are going to see it in the second half of the course, but I'm not interested in really doing fancy 3D graphs, especially because if you're working in 100 dimensions, it doesn't help anyway. So it's not something that I'm encouraging you very hard to study, although they look cool. So maybe you want to do a 3D graph. Have a look. Please. Yes?
I have a question and a remark, maybe. So you said, when you said the error,
yes,
like the approximation error,
yes,
goes down with the sample size. You
yes,
the same dimension, right? So
yeah. Now I'm so this picture here below, still about the 2-dimensional case. So these two are independent things. Okay.
And the second thing, as maybe a solution, maybe not a solution, a possible reason for the approximation, I tried in 3 dimensions and I get 2.1 states, same number of samples. So this is bigger or
No, okay, so.
Would that be because of the pseudo random number and the
No, so did you use the same formula 4 times the number of points inside divided by the number of points?
Oh, yeah.
Okay, so you should change the formula. So what you need to do for the high-dimensional stuff is to go look for the formula of the volume of the sphere in 3, 4, 5, so whatever dimension, substitute radius equal to 1, and then solve for pi, okay, just like we did here. Okay, so you have a formula sort of like this one, where you have substituted r equal 1. Of course, this 2 in this case is 2 to the power of 2. In 3 dimensions, so it's a quarter circle. In 3 dimensions, it would be an eighth of a circle, so there it's 2 to the power of 3 in 3 dimensions and 2 to the power of n in n dimension. That's that. The part here is just the volume of the sphere in 2 dimensions, which is a circle, but the generalization. And you do that in 3, 4, and so on. And that's it, okay? And then you solve for pi just like we did there below. Good. So, are there any further questions? No, apparently not. Good. So, there's another task which I have for you, but first I need to explain some things. And what I need to explain is indexing. Well, before that, let me go through this slide because it's really quick. So these are things that you should look up yourselves. There's also in the tutorial, and there are a few examples. But these are constructors. These three, you should know them, especially the first two, let's say. Should know them very well. This A range is very, very similar to a regular Python range, except that it gives you an array, so it's array range, okay? And it gives, just like regular Python ranges, you use start, stop, and step, okay, as the arguments. And the stop, meaning the end, is excluded, just like in regular ranges. The difference, one big difference is that, well, first one is it gives you arrays instead of ranges. Second one, you can use it with floating points too. Okay, so it's sort of an alternative also to linspace in a sense. You might use it. So depending whether you need to include the endpoint or not, you use one or the other. Depending on whether you know how many the step or just the number of divisions, you use one or the other. So, but they're similar. These things we have seen, they're attributes of an array that you can use to check inside. This fill is used not to construct a new array, but to fill up an existing array with something. Say, for example, if you have an array and you want to reset it to just say start over from all zeros, you use a.fill 0, okay? And that changes the content without creating a new array. It overrides, so it goes writing inside the data. Then there are a few mathematical functions, and they all work as you would expect, by computing the maximum, the minimum, the sum of an array, the mean, the argmax, which is the position where the maximum is. This is the cumulative sum, and there are a few of those, and they work really how you would expect. So just do some things. The important thing here, which I haven't mentioned, is this axis operation. So maybe let's have a look at that. This axis is also ubiquitous. I told you, I think I mentioned at some point that axis in NumPy means it means the dimension. Okay, so in a in a table which is two-dimensional, you have axis 0, which is the rows, and axis 1, which is the columns. Okay, in a one-dimensional thing, you have just one axis, which is 0. In a three-dimensional things, you have the table, which is axis 0, then the rows, which is axis 1, and then the columns, which is axis 2. Okay, so let's see. I'll restart the kernel just to start from scratch. Import NumPy as NP. Now let's create an array, and let's create something like 2, 4, 6, I don't know, 0, 7, 1, just some small thing for doing experiments. not rand, I'm sorry, I got confused, array. Okay, so here we have our array. Now, as we've seen, you can compute the sum of it with either with np.sum a or with a.sum. It's the same. So if you do it, even if the array is two-dimensional, it gives you the sum of the whole thing. 2 plus 4 plus 6 plus this. So it sums everything up, as you would expect, I suppose, the sum of the whole thing. But if you give it an axis argument, so 0, what that means is compute, so axis 0 is the rows. And it means compute the sum along the rows. Okay, so it means, look at the result, it means 2 plus 0, you get 2, 4 plus 7, you get 11, 6 plus 1, you get 7. Okay? Easy enough, except that it's always tricky to remember which axis is which, and when you're in the middle of writing a code and you say, I want to sum along the rows or along the columns, I mean, at least for me, I always forget which is which, and just as an advice, just do something like this. So build up a little example, and then start working your way toward the solution in the console, and then you can put everything in the actual code that you're writing. So if you go for axis 1, it means along the columns, 2 plus 4 plus 6, you get 12, and 0 plus 7 plus 1, you get 8. Notice that in both cases, you get one-dimensional things, because you have removed one dimension, which is the one that you're summing over. Okay? And this is the same. So, of course, this works with max, say. It gives you the maximum along the columns here, which means the maximum here is 6, and the maximum here is 7. You see? There we go. Okay, so this is the axis argument. Any questions? Don't think so. Easy enough. Okay. Yeah, indexing. Now, a little bit of tedious stuff, but I'll leave most of it to your own study. But I need to mention one thing in particular which is important to notice and relevant. So, first of all, indexing. Indexing and the arrays. Now, there are several ways to index. The first one is using scalars, which means the very regular indexing that you are used. Suppose that you have V, which is a vector. Let's say, now I'm working with arrays, okay? So even though I write them as lists, you should imagine that they are really arrays. And so, well, no, remove the commas perhaps, so that at least. And then suppose that I have a matrix, which is 6, 0, 3, 1, 9, 5, whatever. Okay, something like this. So indexing with scalars, of course, with a vector, you can write something like this. So let's say v of 1, for example, that's just 2. And m, in a matrix, you just use 2 indices. So for example, 1, 2 would be 5 in this case. Okay? Row 1, which is the second one, column 2, which is the third one, which is here. Okay, so now there are also one other familiar method which is familiar with you is with ranges, slices, let's say. Slices means something like this, or something like this. So maybe, let's say v of 0, 2, that this would mean 3, 2, and m of, let's say, all this and 0, 2 this would be 6019. Okay, so what I'm writing here, you should be used to this from Python lists. Come on. So this means all the rows. Okay, and then this means columns, 0 and 1. Okay, good. Now, this, I suppose, should be easy enough. There's a tricky thing here, going on here, because this is what happens here is that what you get is a so-called view, and we'll speak in a second about what a view is. But for now, let's skip it. Now, the other way in which you can index things is through lists. And so, for example, you can insert inside the brackets for the indexing, you can insert a list of indices. So, for example, suppose that you write, let's do this. So this is 0, 1, 2. This is 0, 1, 2, 0, 1. Okay, a list here, for example, it could be 1, 2, 0, for example. Okay, and this would give you the element at position 1, and then 2, and then 0, which is 2, 7, 3. Okay, do you see it? And M, of course, you can say, you can even mix it and say all the rows, but in the columns, just give me columns 0 and 2, for example. Okay? And this would give you 6, 1, 3, 5. Okay? And this is not a view. And of course, I haven't told you what a view is, so you don't know what I'm talking about, but you'll see it later. I'll just write it down there for later. Okay, by the way, you see columns 0, 2. In this case, you could have written them with a range, with a slice, actually. How do you write that with a slice? 0, 2 with a slice? Yes, with a step of 2. So 0, you could write, for example, 0, colon 4, colon 2. So something like that. Or 0, colon 3. Okay, and you see, well, there's a difference between the two, which is not apparent immediately, but it's because of this, which I'll explain in a second. Now, just to conclude, the other thing that you can use is Boolean masking. Boolean masking is pretty similar to lists, to the last one. Okay, so Boolean masking. So this consists in using as an indexing expression, using an array or a list of, more usefully, more commonly an array of Boolean values of the same length as the vector that you're indexing in this case. And the idea, so suppose that you do this. Let me call it TFT. Of course, I'm meaning true, false, true. Okay? Now, what that means is that you imagine having the vector on top, let's say 3, 2, 7, and then having this mask, say TFT, and then going through the mask, let's say in this way, okay? Going through the mask and only saving those values where there's a true and discarding the rest. So in the end, what you get out of here is something that looks like 3, 7. The same can be done for example, with the matrix, suppose again I take all of the rows, and then the columns again I take T, F, T, okay, something like this. And what that means is out of 6, 0, 3, 1, 9, 5, then what you do is take all the rows, so yeah, this is like true and true in a sense, and this is true, false, true, and you see that you only save up these two, and so the outcome is 6, 1, 3, 5, okay? Something like this. Now, having said that, suppose that I tell you, as a final task for this Monte Carlo thing, I want to use that as an exercise, use bool masking to plot the points inside the quarter circle in a different color. One line of code. So Boolean masking allows you to select a subset from an array. You have an array, you want to select only certain elements where some property is true, you create a mask where that, and you use that to filter out the array. Good, easy enough, but just for fun. Okay, of course you might want to use not too many points, but whatever. Okay, so this is Boolean masking. And I'll let you look up all the rules then, and also there are examples here. Here somewhere there are other examples. Now, yes, the notes are online.
No, not the I mean the,
These ones. Yes, I will upload them. I will upload them. So I didn't so far, but I will upload this. What I was saying? Yes. So let's speak for a second about views and not views, because this is tricky. You see, it's in red here. Okay, we have the array A. Okay. We have this array A, and I said here, where is it? Here, I can use, for example, an expression like this. Okay, all the rows and some columns. So let's see, all the rows, and then the columns 0 to 2, which means the first two columns. And as promised, you get out an array, which is just a part of the initial one. And you call it that SA. Okay, and then you have this SA, which you can treat as a normal array. You can have the type of SA, it's a normal array. Now you change something, okay? So for example, you take the first element, which is used to be a 2, and you say 0, 0 equals to 88, okay? And you look at this, and it worked. Good. Now you look at the original array, it has changed too. Okay, what this means is that this SA, this subarray, is in memory, is not independent from the original array. If you change one, you change the other because it's not independent data. This does not happen with lists. Look, in a Python list, you have 3, 2, 3, 5, 6, 3, whatever, and then you take a sublist and take L02 again, and sub L as the first two element, and sub L of 0 you can change it to 88, and it has changed, but the original list did not, because this, so this aspect here is done mostly for efficiency. The fact that SA, in this case, this expression here, it gives you something which is not new memory. It's a view on the same memory as before. So you take, in here, in this picture, so at this point it means that we need to revise a little bit this picture that we had here. Okay, so let's revise this. Or rather, yeah, the more high-level description, that would be this. Okay, so revising this a little bit, this is how it actually looks like. Okay, so this is what we had. Now, what it really looks like is that there is indeed somewhere a storage, and then a header with the information which we said is actually a little bit more fine-grained than this. So there's the, say, the type, and then there's shape, and so on, and other things. But the data is elsewhere, and there's yet another pointer here. Okay? Now, when you create a view, what happens? What happens is that there could be some other position in memory. Let's say that here the memory continues, okay? I cannot draw it next to that, but this is still the same RAM going on here off the side. Okay, at some point you create a view of the other array. That's another header, but that other header has different information, for example, a different length, and it points to the same data as before. It's just that it's looking at that data differently. In the particular case that I had in here, so of A, which was this, and sub A, which was this, in that case there, if you think about it, the storage is 88 originally, it's 88,4,6,0,7,1. Now, and this is divided up into, say, first row, second row, okay? This was the original arrangement. Now the view, it looks like this. There's a first row here, then there's a gap, and then there's another row. But, so this gap here is related to something called the stride. I don't care that you really know this term or the actual rules inside there. It's not too useful. It could be useful, but not too much. The real point to understand is that when NumPy, when you use an indexing expression, and NumPy is able to reuse the same memory, just viewing it still as some sort of organized space in regular intervals, maybe regularly spaced, maybe not contiguous, like here. Okay, this is not. So like here, these are not contiguous, but still they're regular. Okay, if you had one more row and you did the same, you would get something. So if the original array had one more row and you did the same expression, you would still get the first two columns. So it's still regular. In that case, you get a view, which means you get the data is not duplicated because it's slow to copy all the data. Instead, you get something that refers to the same data through another object. And so abstractly, you can think of when you have an array, let's say A, you can think of it as pointing to some header, that it turns points to some data. And then when you have a subarray, you can have something with a different header, so it's a different Python object, but then it points to the same data, something like conceptually, okay? And if you don't want that, you must explicitly ask for a copy, so to separate the thing. So instead of SA equal to, let's say, copy of A, you can do it with just adding dot copy at the end. And now CA is this, and you can change CA to 999. CA has changed, and A has not changed, because now I have asked for a copy, which is separated out the memory, copied it, of course, which of course can be expensive, but it depends on your needs. Okay, so this is a view. With slices, you normally get views. Whenever you involve lists or Boolean masks, you normally get independent data. This is the rule. The rules are explained in more detail here. Okay, here are the rules. When I say you don't get views, I should be more precise and say you don't get views of the original thing. There are technical details inside here, but the point to keep in mind is that if you use any lists or masks in indexing, if you use any lists or masks in indexing, then you get some separate data from the original one. Okay? These are the rules. And finally, okay, so questions about this? I know this is a lot. Next time we'll start doing some more fun things. Okay. Final thing is about broadcasting. I've mentioned it already. It's very powerful. It's more powerful than you would imagine if you just thought about it. We've seen some examples in which you can compress whole for loops in a single line of code. There's more. So the basics are what we said before, element-wise operations, either with normal standard operators like plus, times, and so on. Oh, by the way, sorry, just to mention, I sneaked in something before, so I want to point this out. You remember when we did, say, we did axis, which is np.random.random, let's say 5, okay? We had a vector of values, and we said this to the power of 2. It just takes the power of 2 of element by element. Now, actually, the way you could think about it is something like this. Ones of 5 in this case, or maybe, you know, fill no documentation, np.fill. It's not there. So if I do this, full, yes. Sorry. Okay, full shape and value. So 5 filled with 2. Okay, so T is now an array of 5 elements we filled with 2. This is another constructor, which you could do also like this, an array of ones, and then multiply by 2. In this case, you get floating points. Okay, this also works. Anyway, the point is that I have x's, and then I can do x's to the power of 2. You could write it this way. So you have 2 arrays and an operation in between, and it does it element-wise. The fact that this works is just an instance of broadcasting again. This 2 gets broadcasted. Okay? So yeah, this 2 gets broadcasted just like these 3 here we saw before. Good. Now, here's one which is not as intuitive. Here I have a matrix on one side, and I'm trying to multiply it by a vector, which is, I mean, first of all, this does not at all do matrix vector multiplication like in linear algebra. Okay, forget about that. If you want that, there's a special operator, this one here. Okay, you can look it up. It's a @ symbol that is used for, in NumPy, for a sort of like matrix multiplication, matrix vector multiplication, vector scalar product, these kind of things, but not the usual product. Okay, so suppose that you're doing this. What happens, even though it wouldn't make sense mathematically, this, can you stop this? Even though this would not make sense mathematically, this still gets inflated. So broadcasting also, again, just like scalars get inflated, expanded, this NumPy notices that it is a different shape, but the difference in the shape is only along the first dimensions, the rows, in which one has 2 and the other one has 1. So, and on the other axis, there's 3 and 3, so they're compatible. Which means that NumPy can take the first axis, axis 0 here, sorry, and multiply it, so inflate it. And so it gets duplicated like this, like you see below. Okay? And after that, everything works as before. Okay? And now even, so it's extended in a sense such that the shape can be compatible. If this, sorry, where is it? If this second vector had length 4, it wouldn't be possible, of course. If you try to multiply a 2 by 3 matrix times a 5 by 3 matrix, then you have 3 and 5, and Python doesn't know what to do. But if you have 3 and 1, or 1 and 5, and so on, then the 1 becomes replicated, as long as all the other dimensions are either equal or are still in the same situations where one is just 1 and the other is not. So where there's a 1, essentially, it can get replicated. And in fact, even less basics, look at this. This has 2 rows, 1 column. The other one has 1 row, 3 columns. But if you compare them, these can be as just 1 in the dimension of the column, so it can be replicated 3 times. The other one has just 1 row, and so it can be replicated 2 times. And so this first one gets inflated on the axis 1. This gets inflated on axis 0. And after that, everything works as before, element-wise. Which is useful, because this is a little trick that allows you to think of it this way. Suppose I have the same example there, 3 and 1, and I write it this way, and 2, 4, 0 here. And look at the result. 3 by 2 is here. Okay, if you look here, 3 times 2, then you have 3 times 4, then you have 3 times 0. So you see here you have 1 times 2, 1 times 4, 1 times 0. So in this sense, you're building a multiplication table of these 2 things. Now, that's just for multiplication, but whatever operation you do, it works the same. So you have a few elements on one side, you have a few other numbers on the other. You want to do an operation with all possible combinations of one versus the other. You can do it this way with 1 line of code, essentially. Okay? As long as the operation broadcasts. And which is most operations. And if you have an operation that you want to do yourself, this is gone. If you can manage to build to build an operation in terms of basic broadcasting operations, NumPy operations, then you're done. Okay, so we're almost done. I'm letting you go, but I just mentioned this. This is important. The slides have additional remarks and examples. You can finish them up yourselves. What I mentioned are the important parts. If you want to know the general rules in detail, they are here, if you want to read them up, okay, and do experiments. Second, I will give you exercises on all of this part, not just the tasks that I gave you, the PDFs. You do them at your own pace. There are quite a few of those. Sorry.
When will they be?
I'm sorry. Can you?
When will they be posted?
I'm sorry. I cannot. I just between the mask and the noise, I cannot hear. Please be quiet just for 10 more seconds. Yes.
So when will you post?
Please be quiet 10 more seconds. Thank you.
When will you post the exercise?
Like today. I don't know, something. Today, tomorrow, something like that. So, okay. That's it. Yeah. I said all I had to say.